Hey, welcome to the NeuroGuard, where innovation meets compassion, where code meets care, and where today's technology paves the way for tomorrow's solutions. As we mark World Epilepsy Day, we come together in a shared mission to light up the darkness that epilepsy costs over millions of lives worldwide. Hello and greeting to all out there. I'm Mohammed Sayah, and today is not just another day. Today is a beacon of hope, a day that unites us all in a common goal. We're here to unveil something truly special, which is the NeuroGuard, the open source vanguard, the shield against seizures, the project that uh, have the spirit uh, of how we can give back to the community and the power of technology to transfer lives. So in this video, we dive deep into the heart of NeuroGuard, which is a machine learning-based Seizure, Prognosis, and prevention system that harness the potential of transcutaneous auricular vagus nerve stimulation, or known as TAVNS for short. This cutting-edge tool is not just about predicting seizures, it's about preventing them, offering a new lease on life for those afflicted with epilepsy. Joining are great minds from the realms of neurotechnology, machine learning, along of um, the curious individual and the individual also who live with epilepsy every day. Together, we will explore the NeuroGuard and the challenges faced, the milestones achieved, and the path that lies ahead. If your heart beats for breakthroughs in healthcare, if your mind is ignited by the possibilities of AI, if you believe in the power of technology to make difference, then we invite you to be part of this noble journey. Let's collaborate, contribute, and make a lasting impact. Because when we work together, we can do more than just save lives. We can elevate them to new height. So tune with us and get inspired and discover how uh, your skills and passion can join forces with NeuroGuard to create a future where no one has to live in the shadow of epilepsy. So stay with us important is the life-saving adventure, and remember, every life could counts, every insight matters, and every contribution brings us one step closer to a Caesar-free tomorrow. This is the New Guard, and what we are doing for coding for a cause and innovating for an impact. Let's deep dive in New Guard. So uh, let's have like an intro for the epilepsy. So epilepsy affect nearly 1% of the world population, and is characterized by the occurrence of spontaneous seizures for many patients. Um, so um, the rhythm medication can be given at a sufficient high dose to prevent seizures, but patients frequently suffer from side effects. For 20 or 40% of patients with epilepsy, medication are not effective. Even after a surgical removal of epilepsy, many patients continue to experience the spontaneous seizures. Despite the fact that seizures occur infrequently, patients with epilepsy experience persistent anxiety due to the possibility of seizure occurring. So what we are trying to do that is to try to have like a seizure forecasting system or seizure forecasting algorithm that can have a potential to help patients with epilepsy lead more normal life. In order for electrical brain activity, which is the EEG, they recorded from an EEG system. So the electrical activity of the Caesar forecasting system has to work effectively. So we try to find any computational algorithm that which must rarely be identify periods of increased probability of seizure occurrence. If these seizure permissive brain states can be identified, for example, the preactal, which is the instant which period the actal state, which is the actual seizure state, if we can predict that, um, these seizure permissive brain states, we can identify or device are designed to warn the patient of emitting a seizure, or we can using the transcutaneous auricular vagus nerve stimulation to stimulate the vagus nerve and to prevent the occurring of the epilepsy. So this is the like we try to prevent or to reduce the seizure episodes and to minimize the side effects. So let's dig deep on our methodology. First thing we gather or collecting the data. The data actually we use um, is from the Sienna Scalp EEG datasets. This is a well-known EEG dataset, which is captured from a scalp EEG patterns or from a EEG device. Uh, uh, we s- Actually we select the scalp EEG as to mimic the what are currently for commercial shelf EEG devices or headsets that can be used for the patient as a wearable device. Uh, for sure, the most accurate and the most consistent EEG without any further adding noise or adding some of artifacts is the intracranial EEG. But for this purpose of the project that we try to have like a wearable device, which the one the EEG headset and the other one which is the vagus nerve stimulator, to help the patient to have like a wearable device that can be used uh, to seize the epilepsy episodes that can occur. So, so that's why we select the Science-Scope EEG database, and we find that the wonderful metadata that have been extracted from the Cyanoscope, and this is we were going to be used as the labels for our dataset to be trained by the machine learning model. Um, so thanks for the team that from Gupta all to do these annotations and meta data preparation for this data set specifically. That actually they do it to split for patient interest specific, and it is to like to have a specific state of the Caesar types and the different types according to the patient IDs, and they separated to four actal states or four Caesar states, which is the preactal, actal, and postactal, and the periactal. So as to introduce for the for someone maybe that do not have these terms, so we the preactal the states that's before the Caesar. Uh, this is depending on it, depending on different patients. Could be like 10 seconds before, maybe like a day, maybe even weeks. So this is what we are actually we try to target it as to have like a more forecasting or predicting of the theater to be occurred. The ictal is the state, actually the Caesar state, and then the post-ictal after the Caesar state. The pre-ictal is from the starting of the ictal state until to the post-ictal, and this we can call it as pre-ictal. So these are the four states of the Caesars, and and that is the annotated and labeled by Captain All. So this is uh, labeling and classifying the data set into different Caesar types. So we have three different Caesar types in this database, and actually it have been annotated and labeled. We have they offer the patient non-specific, and which is like the whole 46 state 46 records from four different ictal states. And this is not like if you do not like need to the machine learning to know what is the type of the Caesar, so you can directly go for the patient non-specific folder, which is contain uh, per each folder the different state Caesar state. So actually, we depend on the metadata in the provided CSV file, which actually is named as Sienna database timestamp, and this the occurrence of each states have been annotated to a timestamp, and this is the most important thing that we use in the data in the initial data analysis and exploration, and then we use it to extract the different states and provided them to the machine learning to train on that as to identify the different states. So actually, now we do not have like four states. We have like main three Caesar states. So we drop the periectal, which is the total length of the Caesar state from ectal to post-ectal. So we discard that. We take the pre-ectal, the ectal, and post-ectal, and we add the fourth one is the normal. So we extract the normal EEG for each patient. I'd like to have what normal looks like. So in trying to do a feature engineering, a feature extraction from the EEG signals that have been recorded, so we try to like extract a relevant feature to different states, and we are focusing it about the pre-ectal and ectal and post-ectal. We try to have a new, not so really new, but one of used method to have like a feature for. So we select the capture analysis. So to know more about the feature, the spectrum analysis or the spectral analysis is actually that a signal processing technique commonly used to analyze spectral properties of signal, and the term of capstone was derived by reversing um, the fairfold letters of a spectrum. So what a spectrum it reverses to be like a capstone to indicate that the process is a transformation of a spectrum. The process of obtaining a capstone involved different steps, for example, like a Fourier transformation, which is to compute the Fourier transform of the signal to move from the time domain to frequency domain. So that is a transformation step, and then we have like a logarithmic or scaling step that takes the logarithm of the magnitude of the Fourier transform, and this step is crucial as it compresses the dynamic range of the spectrum and emphasizes the periodicities. Then we take the inverse Fourier transformation, or use the inverse Fourier transform, and apply the inverse Fourier transform to the logarithmic of the magnitude of the spectrum, and the result is the capstone of the signal. Uh, actually, capstone analysis have a several applications. One of the most notable and one of the most known for the capstone analysis is the speech processing, where it can be used to separate the effect of vocal tract from the excitation signal. And this is because the vocal tract uh, introduce periodicity formants into the speech signal, which appear as peaks in the capstone. These peaks can called equivalencies values, term also derived from doubling the rate of frequency. So the frequency is equivalency, so that we can use that in like a speech recognition states and know what the who are speaking. So this is like the most common application which actually capture analysis find a way in it. The we have something like called a mel frequency capture coefficient because actually with our features we gather the MFCCS, which is the mel frequency capture coefficients, um, and there are the coefficients that make up the mel frequencies capture, and they are derived from the type of capture representation of audio signals, which is like a nonlinear spectrum of the spectrum. So that is actually we can identify it as like the spectrum of a spectrum. The difference between the standard spectrum and the MFCCs is the later use a Mel scale frequency analysis. So quickly to step like to calculate the MFCs, so we apply some of the pre-emphasized filter, like for example amplification, high frequency, some of filtering. Then we do the framing or slide the signal into short frames. For example, like a 25 millisecond frame with like a 10 millisecond steps, and this is like a parametric thing that you can use it um, um, to fed the best frame that we require to a specific signal. Windowing, and this is like applying a window function, for example, like Hamming window and with the different window filters to each frame to minimize the signal discontinuities at the beginning and the end of each frame. Then we have like the Fourier transformation or Fourier transform that compute the Fourier transform of each windowed frame to obtain the frequency spectrum. Then we have to then this step, which is actually step five, that to do the Mel filter bank, which is pass the spectrum through series of filters known as the Mel filter bank, and this step is convert the frequency scale to a Mel scale, which is a scale that approximates the human ear response to different frequency. Then we take the logarithm of all filter banks energies to capture them. Then we use industrial cosine transformation or DCT, and apply the DCT to the log filter bank energies to obtain the capture coefficient. And also DCT helps to decolorate the filter bank coefficients and yield compressed representation of the filter banks itself. So then the last step is to calculate the MFCs is takes the first DCT coefficients are kept and they represent the signal broad spectrum shape, which is the shape of the spectrum itself, and higher order coefficient are discarded. They represent like the final spectrum details, which is maybe less useful for a speech recognition or other analysis. And in our case, also EEGs, we do not like need to. We need the most broad spectrum shape changes rather than the final one. So that is regarding to how we get to our for the feature engineering, how we can transform our EEG signals to a features which actually is MFCs. We select a number of 20 MFCs, so we have like a 20 MFCs, and we selected a 15 channel, and we will get that further along this video why we choose this specific 15 channels. So we have like a numbers of 15 times 20, so we have like a 300 feature that can represent the different states from the EEG signals. This third step, which is model development, and actually we test different models. We test the support vector machine model, random forest, and balanced random forest because we actually facing an imbalanced class, and we're going to get zero when we are talking to the machine learning model. And we have like we actually also explore deep neural networks, which is the recurrent neural network, which is a sequential LSTM, long short-term memory networks, and also the convolution neural network have been find a place, and actually, well, more pure than the RNN in our classification problem. And these to classify different four states, which is the preactal, actal, postactal, and normal. Then we validate the model. Actually, we try the different like a k-fold cross validation from Gretcher's cross validation. It took a lot of time to do so, and we have like individual evaluation different from different models, and to select what's the best fit actually. By the way, we extend the posting, so posting algorithm in the machine learning. So we explore the ADA post and we explore the AG post, um, and uh, in addition to this the previous model that we talked about. Um, um, this, actually, the objective of this project not only in finding the correct algorithms to identify the pre-actor and to forecast it, but actually is to integrate with a stimulator device that can stimulate the TA, vagal nervous, vagal nerve, to stimulate it and to try um, from the detection of the pre-actor state start the stimulation and to prevent the epilepsy to be occurred. So we have like we sort of the closed loop control system design and which implementing a real-time monitoring system to process the EEG and then try to predict either state uh, of pre-active state or the patient going to have a seizure or something like that and try to give the appropriate stimulation. In this video, we are going to focus on the machine learning models and the algorithms because the integration to a device that is needed an extra research and to identify what is the best parameters of the excitations or stimulation signal in terms of the time and frequencies and all of that. It should be like an under research topic to identify what is the best stimulation um, of the TAVNS. Um, so, by the way, this will going. We can make like as a simulation app. We actually do a simple simulation app which simulate the captured signals to be streamed in 10-second periods to have like in each 10 second you do an analysis and do the prediction if there is an active state or not, and then you have the model to tell you which state is now, and accordingly we're going to trigger the TMVNS stimulator. There is a cool project actually that I will update the Bravo with this is also a a simulation app which simulate a commercial off the shelf TAV and as device, and so you can have a software simulation of the whole system to like to explore and to experiment more. Actually, if this project go further and try to get in more insights, so we need like clinical trial. First, we have like to maybe to test on an animal model, and then have to see to see the to ensure the safety of the system and how this is uh, safe to be applied on human. Then, if yeah, let's see if we were going to the ordinary states of designing a biomedical system that I have like clinical trials and from 1, 2, and 3 until you reach that you are 100% sure that the system is working and they do not have an adverse effect. Um, okay, so actually the potential challenges and maybe like a solution that have been occur to systems that can forecast Caesar. That is should differentiate. The system should differentiate between preictal and interictal states, and this is very important step. And this is actually the key success for such a system. Because if we have forecasting a preictal state very accurately, so we can do what is the most effective thing is to prevent the seizure before happening, and this is like the ultimate goal is to provide some sort of that. So um, so the differentiation between pre-actal and different interactive states is very important and very crucial. So like techniques like for CNAs we see actually when we go further we see that CNAs perform very good rather than the recurrent neural network. Um, the second challenge of this project is the latency in the closed system and the closed loop system. The so the system must be designed for minimal processing time, and the machine model should be optimized for speed without compromising the accuracy. This is the second challenge when we do the integration with the device itself. Then the patient safety. This is important things, and that continuous monitoring and strengthened safety protocols should be very clever to be very clever engineer in the device. And this is the role actually of the paramedical system engineer, which will uh, yeah do a lot of things to do not compromise the patient safety. Um, okay, so let's get started into the code itself. For a quick tutorial demo on the code, and you can to start more and to contribute furthermore. Actually, the repo in the GitHub is NeuroGuard, and um, you can clone it, and then you can cd and yeah curate your environment and prepare the environment that you're gonna to use, and then activate the virtual environment and install the packages. There are the different packages we use, for example the pandas, NumPy, the matplotlib, seaborn, scikit-learn, plotly, scipher, the known library for the data science suits, and we add the libcorsa, which is the signal processing and audio processing library. It's actually very good library, Python library uh, that we use actually to do the signal processing and the Kipstrom analysis. Um, um, then we have the super duper library, which is M&E library. This is well known for the anyone that do brain or neuroscience, computational neuroscience. This is a Python library which give you a lot of tools to process the EEG signals and to have more further insights and to do research using these tools. Yeah, this is a perfect tool, and yeah, I think that is a very common tool used by the um, a computational neuroscientist. So you were going to run different notebooks, which is in the repo to explore it and to know furthermore about it. Maybe you can contribute. You can contribute in different, like for example, improving the app itself. Because I created very simple Streamlit app, which simulate the EEG signal from an EDF file extension, and then we're framing it to have like a 10 second stream-like EEG signal, and then we do a processing state, the pre-processing state, and then we do the prediction step, and finally we output the interpret state. I will show you the application. Um, the for like when you run the Streamlit, the app can provide you that to like to enter to predict the different state from a stream signal, and then the simulation, as we said, like is streaming a 10 sec of the data, to predict the whatever the state and print the output. Also, you can select between different models um, um, to predict the state as to see the how the model will perform in a plant test data. For example, we have like the SVM random forest, balanced random forest, ADA-boost and XG-boost, and the CNN, and we exclude the RNN from. Actually, we train the model on LSTM, sequential LSTM, RNN network, RNN, but we exclude it because actually it have a poor performance if we compare it to other. Yeah. Okay. So let's start with the data analysis and visualization. Um, so the Cyanoscope EEG database it's have a notation of anonymous patient ID, and in each patient folder, it have a different .edf file which contain the a recording of more than 34 channel of EEG data in different registration states of the seizure occurrence for this specific patient. So we load the EDF file by using the mini library and the extensions for the input output read raw EDF because our file is EDF. Then we have the raw data. The raw data we can print the infos of the data as we see here to see the channel names, how many channels contributing into the EDF file, and the some of the information that you know that what is the high pass and low pass. We determine the actually the the frequencies of the total an average of these uh, frequencies that occurs in the file. Also, sorry for that. Also, we have the very important things that we were going to use it and further in the signal processing, the sample frequency, and by default, so this info is in the CNL database. Have a separate .txt file which contain, for example, the Caesar timestamp from start and end, but not actually annotated for each channel. For each channel, yeah. And also not annotated for different states. So it's like to have this is the registration time, and this is the start of the Caesar, this is the end of Caesar, and that is. But in what the team got an all do, they actually provide more depth meta-analysis on the data set itself. So they provide more timestamps for different states: pre-active, active, post-active, and pre-active. Um, so this is the names of channel. So we know the name channel as like to when we do like a further processing of the channel, and we will go to explain that in the next couple of minutes. Um, so we define like a channel pairs because the channel pairs here, um, and that's why actually we as we said that we select the we select actually we select the scalp PG as to uh, put the condition of a wearable device or wearable EEG set that the user can wear, and to like to estimate the different and forecast the projected state. Uh, the the most commercial of the shelf headsets is um, not a research, it's like the commercial one. It have like a 14 channels. So we and in this study we have like a research headset which have more than 35 channels. So we like do actually the in the study of the data set collected that they use a 10-20 system in the electro placement. But what we going to do as per this montage that we have like a bipolar longitudinal referencing. So we And this is why we have defined a channel pairs as to mimic this montage, as to like to have a bipolar referencing. uh, that will decrease the number of channels, because as we said before, that the our feature is uh, 20 MFCs, and we can multiply for each channel, so we have a little feature. So and to reduce the number of channels and to try to make what is most important, so we do the bipolar referencing, and we take those channel pairs as seen in the montage to be used to prepare the channels and how we can do the channel pairs. Then we begin to identify, because actually in the raw data, it's identified all of the channels is EEG, but actually there is like four or five channels that is related to ECG, and some of importance for the like SPO2 or heart rate. So the channels should be uh, pre pre changed for its type from EEG to other types. So we have like we change that. So we have like we select channel 2 as to be the ECG channel, um, and this will be very useful because we will use it to remove the ECG artifact from the EEG signal. Um, we do not have like EOG channel, by the way, so we do not able to remove uh, adequately the blink artifacts from the eye movement. And that actually was very important to record uh, in the raw data set to engage an EEG channel. This is very, yeah, I see that as very important. Okay, so this is a word of describe. So describe these signals in terms of some of statistical meaning. For example, the min, and the max, and the first quartile and third quartile. So we know that if you explore more, if you need like to have like zeros and outliers or something like that, but yet it's a signal, so you can do more signal processing rather than with in a statistical mode. So we have a lot of signal processing techniques that can be used to refine the data. Then we compute the power spectrum density, um, and as we see here, this is show us the power spectrum and how the um, there is like certain changes in the spectrum, and we see the spectrum is not. It's very useful when you decompose it more. But what is useful here, and why we are showing this graph, and actually we see the ECG signal the is defined as the power spectrum. So we need like to remove this artifact as not to unfound that. So to remove it. Yeah. So here we compute with a more handy figure to annotate which of the spike is related to the ECG and how it affects the total power spectrum of the EEG. So as we know now that ECG have an effect on the spectrum, so we will going to have the heartbeat artifact detection and then removal. Many have a very good uh, uh, tool for that. That we can create an ECG epoch from the row by identifying which channel we're going to be contributed, the ECG channel, and try to detect the heartbeat inside the EEG signal. And this is the output, which identifies that there is in a certain epoch that there is a peak of uh, in the side the channels, a different channel spectrum from the EEG, uh, uh, and that we were going to create some of these from the ECG epoch to gain in which ECG signal have been evoked inside inside the EEG signal. First, we will going to do like smooth filtering to remove slow drafts, and we take the low frequency and the high frequency. We take the one and the high frequency none, so we are not like a do band pass filter. So we are setting up like a high pass filter to pass all the frequency more than 1 hertz, and then getting in deep to remove. Um, the other artifacts in ECG. Actually, we do not remove the eye movement because we do not have an EOG channel, so we remove the ECG or heartbeat signal from it. We use the ICA, which is um, it's a component analysis. Okay, and which is called actually independent component analysis. And the independent component analysis is a computational method which separate a multivariate signal into additive subcomponents that are maximally independent from each other. And is actually just very used in signal processing and machine learning tasks. And so like such as, for example, like applying source separation, and we will going to use it to separate the ECG signals as a noise from EEG signal. Actually, how I see it work as the diagram from many. This is diagram from the many library because the many provide an independent component analysis. Um, Actually, it do like assuming the that the observed that signals are linear mixture, and there is a some non-native variable, which is the independent components, and these components are statistically independent from each other, and it's a non-Gaussian. And the objective and the goal is to recover the independent components from the origin signal from the observed mixture of the recorded signals. So we have a mixture between ECG signals that hidden by in the EEG signal. So we need to remove this component from the EEG. So the process include the widening optimization and the algorithm which the ICE depend on it to identify this component and to provide it. As we see here, many implementation is the whitening, and the whitening is including a principal component analysis as to have the dimensional reduction for it and to identify different end components. And the end components we're going to enter through the different algorithm of the independent component analysis. And I think they use a fast ICA, which is a fast independent component analysis algorithms to uh, separate it into end components as the independent components. And then, if we do the ICA dot apply, so we can reconstruct the signal without the component because we can remove here the component, which is the most contributed component, for example, for ECG, and then drop it and reconstruct the sensor back, sensor data to have to have a signal without an ECG artifact, and can be applied for the blind for blinks or eye movement if we use EOG channel. So this is the ICE solution, and we I define different 15 component actually, and we find that the ICE one is the most important, that is mimic the actually get the ECG component here, so we can drop it, and and this is the channel by the way of the actual ECG signal, and we can drop it from drop this first component from this 15 components. This actually this result is after applying the ICA and try to the zeroing out the first ICE component, which is the signal, which is mimic 2 and pretty identifying the ECG signal, and so we drop that and we reconstruct back the ICE. So for example, we have shown the ICE component here. We show the uh, try to exclude the ECG pattern here, and we plot actually the scores. And these scores are very important to each, like in the 15 components. That which one is the most higher, the most like have yeah have like a pattern template with the ECG signal. So find that is the first component, is the most high one, and this is yeah, representing that ECG signal. So we need to drop this component, and if we construct back the signal, so the signal we're going to be without the ECG component inside the EEG data. And here we actually experiment different yeah, if we extend the components and some of that, how it will going to affect, actually it will not affect number of components because we have a single component which is the ECG channels that contributing that. It's very good for other, like for other artifact removal. Then we start after we drop the yeah, sorry for that. After we drop or applying the ICE and drop the signal and construct it back without the EEG, and we found that the signal have been removed, the ECG signal have been removed from the EEG. This is a show. Actually, if we run this script, you will going to find a window, interactive window to see, to scroll on this EEG data. Here we preparing the pipe order referencing. So now we have our raw data on all channels have been removed. We remove the ECG and we do filtering, and let's start to have pick our channels and do a pipe order referencing. So this is a code in how we set the pipe order references, and it's come from actually from the channel pairs that we have identified in uh, the first line of the Jupyter notebook, and we have like identify in the that's the first channel, and the second channel is the first one is the anode, and the second channel is the cathode, to do the pipe order referencing. And using the many set pipe order referencing, and we set the pipe order reference reconstructed raw data, and then yeah, we plot it with um, the signal with the row which is have include all the channels, and we plot the one that which is the do the referencing, for example FP1 with F7, F7 S with T3, and yeah, and so on until, so we have like now from 34 channel to 15 channel. Then we compute the power spectrum density for that to see what is shown, and after that we do oversample temporal projection, which is actual filtration data. It's an extra filtration step for moving artifact, but actually is very good for the streaming data. The still raw data you can do it with different techniques and different filtering techniques. So we use uh, the oversample temporal projection, and try to, yeah, smooth out the motion artifact, but still not the optimum things. Um, yeah, then we began to explore the capture analysis on the our data. So we use the Leprosa library, and we have like this function which is compute the capture mel, and this is actually compute the MFCs and return back an MFCs array. So this we clean the we take the clean data which is have been oversampled. No, no, not oversampled actually, which is filtered using the oversample temporal projection. Term oversample is not right as that. And then we um, applying we get from raw info the sample frequency, and then we applying the compute capture mel, which is there is um, uh, inside the Leprosa tool, which is a feature to extract the feature extraction tools, and in the feature extraction tool we have MFC's calculation of features to be extracted from the signal. So we give the function the signals, and we do sampling, the sampler frequency. We must put that, and the how number of mel frequency coefficients you need. So we identify to have like a 20, and by the way, uh, to get feature for each state, as we know the timestamps from the start of the states, from the data set. So we have like the timestamp of start and end of the pre-ectal, and we have the start and end of ectal, and the same for the post-ectal. So we can give the to extract this data only, which is the states from start and end. So extract that, and we can calculate its feature. And this is how we get the features to make the machine learning model to be to train on. Yeah, and that is the code which actually compute the Kepler-Mel, and yeah, appended as a Kepler-Mel feature to have the final Kepler feature for each state, and yeah, append across the data array or data frame which we're going to be used for that training. Actually, that training testing. Yeah, then we here the raw code for capsular analysis, but we do not need that, and we do not use that. We use the Leprosa MSCC's feature extraction as our like a feature extraction scene. Okay, that is for the data analysis. We prepare a script for the data preparation and processing, and this is processing all the Sienna data set to like to prepare, to filter, and to do all the data processing step, and then extract the features, and yeah, append the features to have and also adding a label as to label each states, and with the features. So we have like a 300 features and one column which is the label column. The label column actually is 0, 1, 2, 3, which is the four states. So the 0 is the pre-active state, the 1 is the active state, 2 is the pre-active state, post-active state, and 3 is the normal. Within this file, actually we do a lot of pre-processing steps. We talk about the filtration and pre-processings and all of that. Then we extract the timestamps. These timestamps from the TSV files was provided from Guptonal. Um, yeah, to take the as I said, the pre-actal start time, pre-actal end time, and all of that. So we have the time stamps, and to extract the data from each record, and then we get the normal data. The normal data actually the concatenation between, because we have state of Seizure, and before and after is a normal. So we concatenate the before and after to have like a full normal data for each record. So we have our fourth state, which is the normal state. Then we extract the features, and after the extract for each state, for each actual states, and the normal state, and then we process an all for the all patients and the all feature, and collect all the features, and yeah, export it as a CSV file, which is named as a merged dataset. So we merge all the patient dataset in one large dataset to be used for training and testing. Actually, it's the Sienna database is about more than 20 gigabytes, so it's reduced after all the pre-processing to be like a 3 gigabyte of data, which will going to be used for training and testing. Okay, so that's for the data preparation. Then we have like different experimentation. Let's start with the DNN, which is the deep neural network experimentation. So we As the first thing, we do the dataset load, and we use the GPU to train to run this model using TensorFlow, and um, after taking the dataset, we do some of normalization and standardization as a standard scale with the fit transform and transforms, and we do in the as a pre-actal state is very small in its like in its natures and its inside the dataset, and the different states, if we compare it to the normal state, we find that we have like imbalance class problem. So we try to overcome this imbalance class with two strategies. The first, we try different oversampling techniques, like for the smart and the Edison. But we find the combination between Edison and the and class weighing is very effective and actually help us to improve the metrics of the models. Um, so we prepare if we overcome the imbalance class problem, and then mm, training the RNA model. This is the architecture of the RNA model. It's a sequential architecture using LSTM and a number of dense layers. The activation structure is like softmax. We can yeah we have a lot of parameters we can um, explore in that. Um, then we the optimizer we select Atom, and we do the fat and 10 objects and a patch size of 32. And it's that way. It's a whole of hyperparameters that can be optimized. Uh, yeah. Then we do the evaluation, and this is evaluation of the RNA model. As we see that in the fourth class, the most present. This show us that there is an like impulse class issue because the number of samples of normal is very high. Um, so this is a precision, and we're calling it one score, and this is the ordinary metrics that come from the Auricular matrix module, and we found that the accuracy is not that too big. But we found it like four, around 84 or something like that. Then we yeah then we have like prepare the CNN model, which is a convolutional neural network. You prepare the architecture using the activation rule in the different, for example, for the first dimension convolution, and then the max pool. We use like a size of two max pooling, and then we do flatten and the number of dense layers identified with the activation function of the rule, and the last dense layer is a softmax, and yeah, the training, and this is evaluation, and we find that it's more having more accuracy in regarding to different percentage record on F1 score rather than the RNA is more better. As CNN is more better than RNA, as we see RNN. Okay, so that's for the deep neural network, and then we have like the simulation experiment. Actually, it's containing here in the for the notebook for ML pipeline. This contain like a very different experimentation with different models, but to find the final outcome and how we can you can extract as a model to different extension we use for the normal learning models. We use the Peckle extension of Peckle, and the for the TensorFlow deep neural network we use the .h5. Um, the final experiment, sorry, the final experimentation, which will give us the different accuracy of our model. Yeah, this one I think. yeah, this one. Uh, so we do loop on the different model we identified here using the pipeline. So we use a balanced random forest. We use the SVM. We use the random forest. We use the adipose and the XG boost model, and then give split our data um, to testing and training that set, and then we do the standardization, do class weighing, and the class weighing would more effective in the normal machine learning algorithms, and then do the kind of the training and testing, and then the classification report for each model. For example, this is balanced random forest. Balanced random forest is very good to overcome the imbalance class problem, because the actually do automatically the oversampling and undersampling to overcome this imbalancing. And this is the final accuracy, it's like a 90%. Then we do the SVM, and inside the SVM we can scroll back again. Sorry for that. Yeah. Um, let's return back to the SVM. The final accuracy for the balanced random force is 90, and the SVM is 99, but is not a good for in blind testing. The adipose given 99, the random force gives 99, adipose give 89%, and in the XG boost 99. So the boosting algorithm, uh, both good in blind testing and also the CNN. So balanced random forest, and the post algorithm alone XGB were the best rather than SVM and RNN. Yeah, this is actually the training. Let's see the application and very in like is our application. Um, yeah, you can select whatever the model you can do. So let's select the CNN. You browse the data. For example, we can take like any data. For example, this data. So it's loaded. When it's loaded, we're going to identify in which a given time of data you need like to simulate the stream. Let's just like the whole recorded. Then we start classification, and it's to do the pre-processing steps, which is filtration, ICA, removing the ECG artifact, and then have a reconstructed rule that's it clean, takes 15 channel, and then yeah, extract the features, and from the features giving to the model to predict. Like if you see that the denoising and then smoothing for turned on, yeah, now it start to predict. So we'll see streaming each 10 second and classify each 10 second it's normal or not. Yeah, and we scroll, but we can find if identify for example a pre-ectal for now. The pre-ectal, yes, we have identified one pre-ectal state. We have a post-ectal. Yeah, we identified a single post-ectal, and let's do the ectal states. Yeah, we identify 16 ectal states. Oh, if we exclude one of the post and one for the pre, so we have like a 15 ectal state. Let's yeah, they're now finished, so we can see if ictal states. Actually, we have two ictal states, and we have in the post-ictal, we have two post-ictal states, and if we find what's in ictal, we have 21, and we have like a 2 and 2, so 4. So we have like, for example, more than like an 18, something like that, 18 ictal state. And the rest is a normal state. So that is the simple application with yeah like simulate stream data and given to the model to forecast if these is what they given from different four states. Okay, let's finally we can conclude, and this is the extensive tutorial on how the repo architectures, and actually what we currently do till now, and we wait you to explore more and to contribute in the NeuroGuard, yeah, and to uh, fulfill the most ultimate goal. Thank you, and yeah, goodbye.